So this lesson is on continuity. We've looked at continuity before, but now we're going to use limits and their properties to determine the continuity of a function. We've previously explored limits to determine if limits exist for a specific point on a function. We're now going to use limits to determine if a function as a whole is continuous or discontinuous using our knowledge of limits. This is pretty straightforward, but I thought we could go through it together. A continuous function we talked about is like a polynomial. A function is continuous if it is a smooth curve with no interruptions or breaks. So some examples are a sinusoidal function like this, or a linear function, a polynomial, which we've talked about before, and an absolute value function. In order for a function to be considered continuous, there are three conditions that must be met. So a function f is continuous at a if the following is true. First condition states that the value a is in the domain of f. So for this, remember that a is an x value that you are evaluating when you're looking at a limit. So, so you're approaching a, x is approaching a point a, and a has to be in the domain for the function to be a continuous function. Second criteria is that the limit of f of x as x approaches a exists. So back to our previous lesson on two-sided limits, if the limit from the left-hand side is equal to the limit on the right-hand side and they're approaching the same value, then the limit exists. So that condition has to hold as well. So our third condition states that if the limit of f of x as x approaches a is equal to f of a, then the function is continuous. So we've looked at this property before for polynomial functions. Remember that a polynomial function is always continuous, so at any point if you're looking at a, you could just basically, x is always going to approach a, and you can use that value. So it's the point that you're approximating is pretty much your y value of that function. Now that we've looked at continuous functions, let's look at discontinuous functions. As you could probably guess, a function is considered to be discontinuous if it is not a smooth curve and has at least one interruption or break. Some examples are a rational function. So as you can see, in a rational function we have an asymptote, so that's a clear break. Or a simplified rational. So a simplified rational, we have a whole, and we'll talk about those more a little later. And a piecewise function, as shown here, has a clear break or gap in the function, as you can see. Now let's look at the conditions for discontinuity. So as you can guess, it's just the opposite of continuity. So the function f is discontinuous at a if first condition is that a is not in the domain of f. Second condition is that the limit of f of x as x approaches a doesn't exist. So if you look at the limit from the right hand side and the limit from the left hand side, they might be approaching two different points. And then the third condition is that the limit of f of x as x approaches a does not equal f of a. So a really common case of discontinuous functions are rational functions, and remember that rational functions can be written as r of x, so that's a rational function, is equal to f of x over g of x. So it's two functions that are divided by each other, and then we know that if the denominator g of x is equal to 0, then we have an asymptote. So it's going to be discontinuous, it's g of x equals 0. And then we can also have a whole if you can cancel something out on the numerator and the denominator. So remember that rational functions, and then it becomes a simplified rational. So that was the case we saw in the slide above. Otherwise, it's continuous for every other point that's defined on the domain. So really, we're looking at wholes and asymptotes that are going to be discontinuous for rational functions. Now let's do a couple of examples. For each of the following, determine if the function is continuous. If it's not continuous, state why not and identify the type of discontinuity. So the first function is f of x is equal to 3x to the power 4 minus x. This is a quartic function, and of course it's a polynomial. And you know, with polynomials, the domain is XER, so it's infinite. And we also know that the limit of p of x, which is our polynomial, as x approaches a, is going to be equal to p of a for all the domain. So f of x is continuous. Now let's look at b. F of x is equal to 1 over x minus 2. This looks like a rational function, and for a rational function, you know, the domain in this case is x is an element of the reals such that x cannot equal 2. Because we have a vertical asymptote at 2, so setting the denominator to 0, you know that 2 minus 2 is going to give you 0, so x cannot be equal to 2. So if you look at 2, if a is 2, you know that the limit is not going to exist at that point. So when you look at it from the left-hand side, you're going to look at it from the right-hand side. It's just graphically it's a break, but you know if you look at it from both sides, they're not going to be equal, so the limit doesn't exist. So f of x is discontinuous. The next example is f of x is equal to x squared minus 9 all over x squared plus 5x plus 6. I know you're dying to factor this, so let's go ahead and do that. The numerator looks like it's a difference of squares, so it would be x minus 3 times x plus 3. Sorry about my writing, I'm using my finger. Can't find a stylus, so apologize. The bottom is going to be a trinomial factor, so x plus 3 and x plus 2. So you can already see that we can cancel out the x plus 3, which means that there's a hole at x is equal to negative 3. So we also notice that there's a vertical asymptote at x equals negative 2, since that's already left on the bottom and we can't cancel it out. So the only thing that would make the bottom equals 0 is negative 2. So we have vertical asymptote there. So we have two discontinuities for this function. We have a vertical asymptote at x equals negative 2 and a hole at x equals negative 3. And so the limit of f of x as x approaches negative 2 doesn't exist. The limit as f of x as x approaches negative 3 is 0. So f of x is discontinuous. Okay, our next example. For the piecewise function below, sketch the graph and determine the x values at which the function is discontinuous between negative 10 and 10. So we have a piecewise function here, which looks like this. Okay, that's not so bad. So this function is negative x squared between 0 and 10. So that looks like this, and doesn't include 0, so we have an open hole here. And it's just a parabola pointing downwards. And this is supposed to be a straight line at x plus 20. So it just has it's just a line with a y-intercept of 20. And that occurs from negative 10 to 0. So just imagine from here to here. And then obviously I didn't quite hit my domain, but it's just a sketch. So we can already see that f of x is discontinuous here, and the reason is because the limit of f of x as x approaches 0 doesn't exist. So if we look at it from the left-hand side, we get the value 20. We look at it from the right-hand side, it's approaching 0. So those are two different values, so the limit doesn't exist at x equals 0. For our last example, given the function below, find the value of k if g of x is continuous. So if g of x is continuous, and this is a piecewise function, that means that the limit from the left-hand side has to equal the limit from the right-hand side. So it has to form, like if there's an open circle at one point, it has to be filled in, it has to be continuous. So they have to intersect. So if they're intersecting, we want to find a point of intersection, which is setting them equal to each other. So we can say that the limit of x plus 3 as x approaches 3 will have to be equal to the limit of 2 plus root k. So this is assuming continuity. So now we can just sub in our values. So if we're assuming continuity, we know that x is approaching a, and so we can say that 3 plus 3 is equal to 2 plus root k. Oh, this is so messy, I'm sorry. And now we can solve for k. So 6, move over the 2, you get 4. And so root k, I'll do it here, root k is equal to 4, which means that k is equal to 16. Alright, that's it. Hope that was a continuity of fun.